Good afternoon. My name is Mauricio Sarabia from the Universidad San Sebastián from Chile, and I am presenting on behalf of my co-investigator, Dr. Carmen Gonzalez from TEM, also from Chile. Our work is titled Advanced Bone Implants with Micro-Wrinkled Surface Obtained Through Additive Manufacturing, and is based on the manufacturing and testing of scaffolds for use in tissue engineering, specifically for bone tissue. To do this, we rely on additive manufacturing technology, or commonly known as 3D printing. The advantage of 3D printing over traditional manufacturing techniques is the fact that it allows the manufacture of parts with complex geometries, both internal and external, with very high resolution. This allows us to design and manufacture parts tailored to the needs of each patient. One of the biggest problems with this technology with dynamic printing, which means digital light processing, is that there is not a wide variety of materials with which it can be manufactured using this technology. From this point of view, our work as material scientists in this field is to develop new materials that meet the necessary characteristic to be used as base for these biomedical devices. Our work in particular is based on the synthesis of a biocompatible resin based on the PET graph methodology. This type of route of polymerization allows the reversible degradation of the polymer, making it much more versatile than from the point of view of the structural modification of the compound. In addition, to increase its degree of biodegradation considerably. For this, we mix 5 different concentrations of polyethylene glycol deacrylate, or PECTA, as a cross-linking agent, acrylamide and dimethylaminoethyl methacrylate as main monomers. The chemical analysis of these compounds allow us to determine that the conversion of the monomer into polymer is according to the decrease in the vibration band near to 116 centimeters minus 1, which corresponds to the carbon double bond. In parallel, the rheological properties of the resin were measured, such as the dynamical viscosity, their density, the bond number. In addition to the contact algon, which is formed between the resin and the metal printing plate. These results confirm that there is a good addition between the resin and the metal plate, indicating that the resin will be suitable for printing using the DLP technology. After this, the pieces were printed and their parameters were optimized to obtain pieces with high resolution and very good reproducibility. Once the pieces were printed correctly, the formation of a thin film on the surface of the material was studied to subsequently form the wrinkled polymer film. To achieve this, different rotation speeds and baking times with different film thickness were studied. With these results, it was possible to obtain a wrinkled micropatterns with dimensions varying from 1.6 micrometers wide with an average amplitude of 0.33 micrometers and a roughness of 221.72 nanometers approximately. Finally, the biocompatibility tests were carried out using MCT3 cells cultured in Demen media containing 10% of FBS, 10 millimole of herpes, and 100 units per milliliter of penicillin. The cell viability was determined at different days of incubation, 1, 3, and 7 days. And by using the protocol of Armor Blue, it was possible to measure the the metabolic activity of the cells. After 2 hours of incubation, with the Alamar brew reagent at 37 degrees in a humidified air atmosphere, the medium was collected from the samples and the absorbance was measured at 517 nanometers using a microplate reader. As is possible to observe in this preliminary study, the cells tend to attach and adhere to the sample surface for at least 7 days incubation. The Alamar Blue analysis also allow us to demonstrate that these cells present high metabolic activity, thus indicating promising results in terms of cytocompatibility, cellular proliferation, and adhesion. Thanks.